Can you speak for a second so I can hear?
Hi. Hi. Can you hear me? Can you hear me?
Yes, very, very clearly.
Oh, hi Dan, by the way.
Hi.
You too.
Hi, good to see you.
Hi.
Sorry you couldn't make it, but
Yeah,
I'm glad you could still speak.
right. So sorry about the Monday. I got really confused about the time. And
It's happened to me before. I think one time when I was giving a talk in Germany, I completely screwed it up. I was like really confused. So and I totally understand.
and here it's even more basic than time conversion error is that I looked at the last talk of this conference. It's ending at 2:30. So I assumed my talk would start at 32, but
I see. So I think everyone else they're still getting cookies right now, but maybe I'll round up the crew soon. Sorry, you can
oh,
talk.
hi. Hi, I
Hi,
couldn't hear you. How are you?
I'm good. And you, do you recover yet?
Yeah, I'm almost completely recovered. It's just a runny nose, but I guess the symptoms were minimal, and
Uh-huh.
so it was really annoying to just because of that miss the conference, you know.
Yeah, it's a
Because
pity. We wish you
yeah,
could be there.
yeah, I was not sick enough to I could still travel and things like this, but of course for other people.
So you went to a test after you feel the symptoms, or you had a regular test from university?
So I had a PCR test from a Walgreens.
Oh, okay. But you did your like after you feel something wrong, or you just like the university asks you to do that every week?
No, it's actually because my girlfriend got it and she had some symptoms.
Oh,
Hey, Antoine.
Hey,
I
hello.
see. So you like a self-conscious, you feel like you have to do the test.
Yeah, so I suspected that I got it too, right? Naturally. And right. So actually I did many um, self-testing. I had some self-testing kits and these were all negative. My girlfriend and I tested ourselves 4 times using these things and they were all negative, while actually the PCR tests were all positive. So
Oh, wow.
How are you doing now?
I'm doing really fine. I mean, I'm almost completely recovered. Yeah.
Okay, that's good.
How are you?
Great.
Just same old, same old. Yeah, just go here. Yeah, I think I was just in town,
All
and then
right.
I ran into Antoine, and I was like, oh yeah, let's see each other, and that was I think right exactly around the time
Mm,
I think your girlfriend got positive, right?
yeah. Technically, I was already positive, I think, at that time.
Ah, okay. I mean, I was like I was wearing a mask actually.
Mm.
I think I was wearing a mask. Shoot.
You were.
Yeah. Well,
Oh,
I don't know.
at least you are wearing
Maybe I'll
now.
keep my mask on more right now. I'll sit at
Yeah,
the back.
I definitely will keep my eye on now. There's like a chemical smell around in the basement. I don't know, something is burning here. Probably we have to evacuate to do your talk. It's, so did you messed up the time difference on Monday?
So
Or
actually, what I did was even more stupid than that. So I took a look at the schedule, and the last talk of the conference is ending at something like 2:30. So I assumed my talk would start at 30 and not 10.
oh, I
Just
see 30, but not 410. Yeah, so I see.
Hi, Antoine.
Right.
hi, hi, Christos. Really
How
enjoy your talk, by the way.
Oh, you don't have to say that.
Yeah, I wouldn't say it if I didn't.
Okay.
Tell us the truth.
How are you feeling? I heard you caught COVID.
Yeah, I'm totally recovered. I just have a runny
Okay.
nose sometimes.
Okay, that's good. How long did it last for you?
A few days. I mean, I was sick for maybe 3 days, and now the good thing is I'm immortal, right? I'm invincible.
Yeah.
Yeah, let's start.
All right, everyone, for our last talk of the day, we're very lucky to have Antoine Song, who will be telling us about the spherical plateau problem.
Thank you, Martin. So first, hi, everyone, and I apologize for Monday. It was embarrassing, but I'd like to thank Sin for saving the day. And let's see. So my talk is going to be mostly off topic, but I promise that I'm going to say something about the main theme of the conference toward the end of the talk. But yeah, so if you're here to hear about scalar curvature, then see you later. All right, so what is a spherical plateau problem? It's going to be an infinite codimension plateau problem that I think has some geometric meaning and is interesting, for example, topologically. So what is the general motivation for that? It's actually a question due to Tom and Yao, and I'm sure many other people, and it's very simple. So you start with a closed-oriented manifold, and you want to construct a corresponding metric space. Sorry, so you want to find a best Riemannian metric on M, whatever it means. So by design, this question is an open-ended question, and half of the work is to define what you mean by a best metric. So I'm going to treat a generalized version of that question. It's not reasonable to actually try to construct such a metric on M, but what you want to do instead is you want to get a metric space at the end that reflects a lot of things about the topology of M, and hopefully the metric space is special. So you need to guarantee somehow two things. You want to construct the metric space, you want some existence results, and you want the metric space to be somehow special, right? Maybe it satisfies a PDE, maybe it says a lot about the topology of M. And just as a side remark, so you could think of the Einstein geometry, right? It's very natural. It appeared a lot in the previous talks. So right now for Einstein metrics, what's really hard is that in general dimensions, you have neither of these 2 points. So you don't have general constructions for Einstein metrics in higher dimensions. And it's not clear if the Einstein geometry is related at all to the topology in dimension higher than 4. So higher than, starting from 5 and above. So I'm going to give you another recipe you start with a closed-oriented manifold and you get a metric space at the end. And it's going to be an infinite codimension Plateau problem. So that's the main idea of the talk. I should maybe recall a few basic facts about the Plateau problem. What I mean by Plateau problem is any problem where you try to minimize the volume, a notion of the volume, and you try to construct minimizers of the volume. And the most successful framework is the framework of GMT in finite dimension. So what I'm writing here is that the so-called homological Plateau problem can be solved with the notion of integral currents. So the notion of integral currents is due to DeGiorgi, Federer, Fleming. And what's happening is that if you're given a closed...
Hold on, Antoine, we have a problem. Yeah, there's a building condition in which we will have to pull the fire alarm.
I hope you do not burn. See you later.
But we'll be able to come back, right?
Okay.
Yeah, but we're gonna have to put this on pause for a bit.
Good luck.
Yeah, so sorry about that. But yeah, we'll be back.
So glad you're back. And I was talking about the Plateau problem in finite dimension. So that is the classical case. And again, what you start with is a closed Riemannian manifold, that is the ambient manifold. And then you fix yourself a topological class. So you take any non-trivial, say, homology class. You consider the integral currents inside N that represent that homology class. So if you're not familiar with integral currents, just think of them as generalization of submanifolds. They're just essentially a countable union of Lipschitz manifolds. And now you consider a sequence of such integral currents representing H, such that the mass is converging to the infimum that is allowed by the homology class. So this is the infimum of the mass. By Federer-Fleming compactness theorem, you can find an integral current, C infinity, such that subsequently you have convergence of the Ci to the limit C infinity. And we are going to call that C infinity a Plateau solution corresponding to the homology class. It happens that you not only have the existence of such a current, but also you have a lot of nice regularity. So by a big theorem of Almgren, you can also see the more recent work rewriting of the proof by Dolilis and Spadaro. This infinity is going to be smooth outside of a codimension 2 subset of the support. And this result is optimal. So this is very standard, but from time to time, it's good to appreciate the power of these results, because apart from maybe Taylor geometry and conformal geometry, it's really rare that you can get these such general existence results plus regularity. And so motivated by the success, people were interested in extending this Plateau problem to other metric spaces, or for example, spaces of infinite dimensions. And what I'm going to focus on today is going to be a generalization due to Ambrosio and Kirchheim. So they formalized what's called integral currents inside any metric space. And basically what you can do now is to talk about the Plateau problem in any complete ambient metric space. So their work is based on earlier work of the Georgi and Gromov. And you have a lot of subsequent works. I'm just mentioning a few of them. So Lang, Wenger, Schmidt, Sormani, Wenger, etc. So this is the kind of framework we're interested in today. And let me give you more concretely what we're considering. Fix yourself a separable Hilbert manifold that I'm going to suppose of bounded diameter. And again, fix a homology class. As before, you can look at the integral currents that represent H, this homology class. And as before, you want to consider a sequence that minimizes the mass. Now, because the dimension is infinite, the Ci may not converge even subsequently in any reasonable sense to anything that lies inside the original Hilbert manifold K. So that is something that is due to the infiniteness of the dimension. So what is going to replace the Federer-Fleming compactness theorem? Well, there's this very powerful compactness theorem due to Wenger that works for integral currents in this kind of space. So what is the statement of this compactness theorem? You give yourself a sequence of boundaryless integral currents with uniformly bounded masses and diameters. Then subsequently, this result tells us that there is an abstract Banach space Z, an integral current S infinity inside of Z, and some metric isometric embeddings of your currents, the whole sequence, inside this same Banach space. And inside that Banach space, the push forward of your sequence is converging in a very nice way to S infinity. So this notion of convergence already appeared in the talk of Robin, and it's called intrinsic flat topology. It is to the usual flat topology what Gromov-Hausdorff is to Hausdorff topology. So what you did is you found a Banach space in which you can embed everything, and in that Banach space, everything converges nicely in a classical way somehow. In our case, we can apply that, that compactness embedding. So for our Plateau problem, in particular, there exists a Banach space Z and some isometric embeddings of the whole sequence. plus an integral current C infinity inside this Z, this Banach spacer, that you have this nice convergence of Ci to C infinity subsequently. And we're going to call such a C infinity a Plateau solution for H, in complete analogy to the finite dimensional case. Here you already have some questions. For example, what is the optimal regularity of C infinity? What is the continuity? Do you have continuity of mass under this convergence? So regularity in finite dimension, that's due to Almgren. You have some partial results in infinite dimension, but right now it's not clear if you can get something optimal. And for this continuity question, it's not clear, unlike the finite dimensional case where it's trivial due to the compactness theorem. It's not clear here that you actually have convergence of the masses, meaning the mass of C infinity is the limit of the masses of Ci. At least what's known is that the mass is always lower semi-continuous. So the mass of the limit is going to be bounded from above, but continuity is not clear. And for the regularity of C infinity, if you know already that C infinity, say, is an area minimizing integral current embedded in a Hilbert space, then Ambrosio Deleuze-Schmidt showed that the support is going to be smooth on an open dense subset of the support. And it is kind of plausible that the Almgren theorem holds in this generality, holds for this kind of area minimizing integral current. Right, so these are the tools I'm going to use. And this is a very general theory, but what about a very concrete example? And the first and only, I think, example of an explicit Plateau solution in infinite dimension without boundary is due to 3 people, Besson, Courtois, and Gallo. And their example predates the theory of integral currents in metric spaces. And they found that example when they were proving their famous rigidity theorem. So I'm going to first state the rigidity theorem of Besson, Courtois, and Gallo because it's such a huge theorem. And I'm going to give their example of a Plateau solution in infinite codimension. So let M be a closed-oriented hyperbolic manifold, and you consider the universal cover of M. You fix a point in this universal cover. For metric G on M, you can define the volume entropy of G. What is it? It's just going to be this limit, the limit of the log of the volume of the R ball inside the universal cover, the whole divided by R. And you can check that this limit always exists and it doesn't depend on O. So that's a nice invariant of the metric G. And it's related to the topological entropy in dynamical systems. It has nothing to do with the entropy that appeared in the talk of Robin. The result of Besson, Courtois, Gallo says the following. If you take any metric on M and you rescale it so that the entropy is going to be less or equal than the entropy of the reference hyperbolic metric, then you always have that the volume of M is larger than the volume of the hyperbolic metric on M. Oh, and sorry, so let me mention, let's say dimension at least 3. Then you have rigidity in dimension at least 3. You have equality of the volumes if and only if G is isometric to G0. So first time I saw that result, I was really amazed because the proof uses a kind of Plateau problem. I'm not going to explain how they do that, but they transform that question into a question about minimizing the mass without any constraint, but inside a certain infinite dimensional space. Right, I'm going to come back to that result maybe later, but now I'm going to give you the example of a Plateau solution. Again, same setting, you have the universal cover and you fix a point O, and you denote by partial M tilde the boundary at infinity of M, that's a sphere. So it's, you can endow it with, naturally with a round metric, round measure, the theta. And now you look at the unit sphere inside an L2 space, the L2 space on the boundary at infinity. So that is weird, but okay, why not? Now you let b theta be the Boozman function. If you don't know what it is, it doesn't matter. It's a very classical function and completely explicit in the hyperbolic case. Now you can consider the so-called Bieber-Bach embedding of the universal cover inside that infinite dimension unit sphere. And the formula is given here. So you need to check that indeed this is a function of the unit sphere of L2 norm 1. So it's a function in theta. Theta is an element of the boundary at infinity. This embedding has the good taste of being equivariant. So it gives, by taking the quotient, an embedding of M this time inside the quotient of an infinite dimensional unit sphere. Okay. One thing that you can check is that by symmetry, this is a Riemannian isometry. And secondly, this is a minimal embedding. And that's not so hard to check. You just check locally that the mean curvature is 0. But however, you have much, much better, and that is a theorem of Besson-Courtois-Gallot, the image of M by B is a calibrated submanifold. In particular, since it's calibrated, it minimizes the mass inside its homology class. And so you have here a Plateau solution in the spherical quotient, S partial M over the fundamental group, corresponding to the homology class of that space, given naturally by M. Right, so this is the first and only explicit example, if you want, of purely infinite dimensional Plateau solution. Is there any question about that? Let me mention that it's not clear why they would do that in order to prove their rigidity theorem for the volume entropy, but it turns out that they just transform the inequality that they want to prove here into an estimate of a quantity of the form infimum of the mass inside a homology class. So they need to compute a value like the infimum of the mass inside a homology class of a very specific Hilbert manifold, which is this spherical quotient that I mentioned here. Right, so this is the starting point, and you could say, well, this embedding is extremely specific. You need a lot of symmetry, and you need notion of boundary infinity with Boozman functions, etc. You need a lot of properties of the space. So what about non-locally symmetric manifolds? Say you start with any three-dimensional manifold. And also, what about uniqueness? Because here, what they prove is that you can construct one specific Plateau solution by a specific embedding. It turns out that there exists, it's a fact that there are sequences of currents in the homology class you're considering that are not converging to the image of M and that are trying to minimize the mass. So they're somehow escaping at infinity. So it's really not clear that you have uniqueness a priori of this Plateau solution. So now I want to set up a more general problem because I want to be able to talk about the fundamental group of manifolds and more generally of homology classes of any discrete groups. So I'm going to quickly give you an idea of how the spherical problem is set up. What you want to do is to define a homological Plateau solution for general discrete groups and general group homology classes. So you start with a countable group. And for instance, you can think of it as the fundamental group of a closed-oriented manifold. And you want to construct an ambient Hilbert manifold that is going to be the ambient space, right? So what you do is you're going to find a classifying space for gamma with a canonical Hilbert metric. This is exactly what Besson and Courtois did. What a classifying space is for gamma, it's just the quotient of a weakly contractible space by a proper free action of gamma. So it's, in some sense, topologically, the simplest space with fundamental group equal to the fundamental, equal to gamma. Topologically is going to be the simplest space, but you have non-uniqueness of the geometry. You're going to put a canonical Hilbert metric on it. Then you consider a homology class in that space, and you try to solve the Plateau problem. And my claim is that this is an interesting problem. So what is the choice of classifying space that you're going to make? It's actually the simplest construction of a classifying space I know, and it goes like this. You fix yourself the separable infinite dimensional Hilbert space. That space is unique up to isometry. You're given your countable group. Remember, you want to construct a classifying space for gamma. What you look at is the unit sphere in this L2 space. The unit sphere in the L2 space of from gamma, of functions from gamma to this Hilbert space. Gamma acts isometrically on that sphere by the regular representation. So all of this is very standard. I'm recalling the formula. And what you would like to do essentially is to take the quotient. However, this action is not free. So you're going to just remove the minimum possible from the sphere to get a space on which the action becomes free. So I'm going to call that a new space S star. And a fact that you can check is that the quotient of that space by gamma is a very nice Hilbert manifold because it's a classifying space for gamma. It's not a complete manifold, but it's not going to matter for our purpose. The important thing is that it's a round Hilbert manifold and it's a classifying space for gamma. Right, so for example, if you started with a manifold M, a closed-oriented manifold, then the fundamental group is called gamma, right? And using the previous slide, you can construct a classifying space, which is a nice Hilbert manifold. And because it's a classifying space, you essentially have a unique way to map M into this big space. So that determines a homology class in that big space. And then you try to solve the Plateau problem, meaning you minimize the mass in that homology class. At this point, you might wonder, okay, I presented two spherical quotients. One is due to Besson-Courtegault, and the one here using S star. So what's the relation? For the purpose of this talk, just think of them as essentially the same thing. They're not isometric actually, but the Besson-Courtegault choice lies in a certain closure of my choice, at least when gamma is the specific gamma that they choose, meaning the fundamental group of a hyperbolic manifold. Okay, so let me speed up a bit. The first theorem is a uniqueness theorem. So it says the following: you start with a closed-oriented hyperbolic manifold of dimension at least 3. Then the claim is that any Plateau solution for the canonical homology class it determines in the classifying space is intrinsically isometric to a rescaled hyperbolic metric. And remember, a Plateau solution always exists just by Wenger's theorem. But then the point is to say something interesting about this Plateau solution, right? And what Besson-Courtegault did was essentially to find one Plateau solution that was intrinsically isometric to that space. What I'm saying here is that whatever the sequence, minimizing sequence you choose and the limit that you get, the limit is going to be intrinsically isometric, meaning if you take the length structure or the path metric on that metric space, is going to be isometric to this rescale hyperbolic metric. And you might wonder, well, what happens in dimension 2? In dimension 2, you don't have uniqueness of hyperbolic metrics, and it's paradoxically harder to say something about the uniqueness of the solutions. So the conjecture, the natural conjecture to do is that in dimension 2, so for surfaces of a genus at least 2, any Plateau solution for M is going to be intrinsically isometric to a certain compactification of the space of rescaled hyperbolic metric on the surface. So you would have all the hyperbolic metrics rescaled correctly, plus something in the closure of that space. Okay, before talking about the proof, let me mention quickly what happens in dimension 3 because it's one of the main theorems. So in dimension 3, here you don't have locally symmetric, right? It's just a general closed-oriented 3 manifold. However, by geometrization, it makes sense to define the hyperbolic part. If you don't know geometrization, just think of the hyperbolic part of M as being the topologically and geometrically most important part of your manifold. And it's uniquely determined. It has a unique hyperbolic metric on it. Then what I'm saying here is that in this Plateau problem, you can identify the Plateau solutions. Any Plateau solution for corresponding to your closed-oriented 3 manifold is intrinsically isometric to a rescaled hyperbolic metric. And so the picture is, again, you start with your closed-oriented 3 manifold, you embed it into an infinite dimensional Hilbert manifold that's super easy to construct. You try to minimize the mass, that's the most natural thing to do. And all the limits are carrying some information about the topology. It's giving you back the hyperbolic part of M. So how do you interpret that? So if you know about Ricci flow, recall that Ricci flow, which is the way people prove geometrization in the first place, for Ricci flow, you start with any metric on M, and you, after correctly renormalizing the Ricci flow with surgery, you wait a long time, and at time infinity, what you see is exactly the hyperbolic part. And so the theorem above gives you a completely different interpretation of what the hyperbolic part is. It's going to be the unique solution of a certain Plateau problem. Right, so let me go directly, okay, to the application. So one application that I realized lately, very recently actually, is that all of this enables to show some stability result for the classical volume entropy rigidity result. So for example, in the easiest case of the closed hyperbolic manifold, recall that Bézoncourt-Gallo tells you that for any metric such that the entropy is rescaled so that it's less than the reference entropy, then the volume is going to be larger or at least equal to the volume of the reference model metric, the hyperbolic metric, which is unique in dimension 3 again. And you have equality if and only if G is isometric to G0. So at this point, you might wonder what happens if the volume is extremely close to the reference volume. You want to say that the metric is converging back to G0, right? You want to get the stability result. And what I conjecture, or it's work in progress, is that you have this pretty clean statement, which is, okay, if you take a sequence of metrics on M such that you have this usual condition, and also the volume is converging to the reference volume, you know that it's always larger, or at least equal to. And the claim is, if you have this convergence, then the Riemannian manifolds Gi are converging to, sorry, so here is G0, are converging back to the hyperbolic metric in the intrinsic flat topology, so the topology of Sormani and Wenger. Right, so this is what would follow non-trivially from what I told you above about the uniqueness, intrinsic uniqueness of Plateau solutions. And let me make a little digression here, which is maybe the only part related to this workshop, really. So Dan and Christina, they conjectured a stability result for the positive mass theorem. So you have the positive mass theorem, it's a nice rigidity result, and they conjectured that if the, say the mass, you have all the usual conditions, that if the mass is really close to 0, then in some sense, your space is really close to being flat. And in what sense? Exactly, it's expressed using the intrinsic flat topology. So they had the idea to try to express that using this new topology. And what's interesting is that if you try another topology, so naively, maybe Gromov-Hausdorff, pointed Gromov-Hausdorff, this is completely wrong, right? Because you can add some threads, thin thread, preserving the scalar curvature bound and not modifying the mass. The same thing happens for the volume entropy, the thing that I'm interested in here. If you add some thin threads, it's not going to have any bearing on the volume entropy, which is computed, you remember, by taking the volumes of large holes in the universal cover, etc. So you have the same phenomenon. In order to express a stability result, Gromov-Hausdorff is useless. Okay, for this conjecture, you can look at progress by Lan, Dan, and Christina, with also Raquel Perales and also Jean-Regui. Right. Okay, I'm going to go through that very quickly. So if you have this time a three-dimensional oriented hyperbolic manifold, there is this conjecture of Egel-Storm and Thurston that for any metric on M, any Riemannian metric on M, if the scalar curvature is lower bounded by -6, then you have a bound, an upper bound on the volume entropy. On the other hand, by using Richelieu, Perelman showed that if you have this scalar curvature lower bound, then the volume of M is larger than the volume of the reference canonical metric, hyperbolic metric. So let's stare at that for a second. Remember that Besson, Courtois, and Galoche, they showed that if you have this, you have that. So in particular, if the conjecture of Egel-Storm Thurston is true, then by Besson, Courtois, Galoche, you recover in dimension 3 that result of Perelman. Anyway, so these series of results suggest something, a stability for this time, the scalar curvature. So if you have now a sequence of metrics on M, which is oriented hyperbolic dimension 3, if you have this scalar curvature bound, and this time if the volume converges to the reference volume, then the sequence of metrics converge to the reference metric in the intrinsic flat topology. So by the way, I'm not totally up to date on the conjectures that are written in scalar curvature. So if that's already a known conjecture, please let me know. But this is what really comes supernaturally from what we were discussing, right? And I think I'm going to stop here and see if there's any question.
Okay.
I think it's just a break, right?
Yeah, I didn't. Yeah, people were a little confused. I don't know if you were saying you were ending the talk or you were just saying you're pausing for questions.
Oh, I can end the talk here. Yeah.
No. There's more talk. We want to see it. There was a slight confusion from the wording. That's all.
No, I can't. I'm going to stop here. I'm going to stop.
Okay. All right, so any questions? Antoine, can you remind us what it is that Andre proved about the entropy under that scalar curvature lower bound? Are they close to proving that conjecture? Hegel, Storm, and Thurston?
Yeah, so what they proved is, okay, they have another, say, Caligari, Marcus Neves, they have another kind of entropy that looks like the volume entropy, that's, okay, that, and they can prove this conjecture in the setting of their area, like minimal surface entropy. And actually, the inequality is really not something, let's say it that way. So it's a result of, I think, Ben Lowe and Neves, that if you have a lower bound on scalar curvature, then they have an upper bound that is optimal. So the optimal, I don't remember the exact value, but it's the upper bound that you get using the hyperbolic metric again. And their proof uses really a Ricci flow. Right. So, but I wouldn't say this is close to that conjecture. I mean, formally, of course, it's the same thing, but the entropy that they're considering is vastly different. One is using dimension 2 objects, which behave very well under scalar curvature, right? Minimal surfaces and scalar curvature, great. But in this setting, so the volume entropy is really more related to geodesics, and geodesics and scalar curvature. It's not clear that there's such a tight relation, at least. Hear you. Can someone?
Yeah, the question was the volume entropy can be defined without any curvature assumption?
That's right. The volume entropy is not related to curvature. However, in the other way, so if the Ricci curvature is lower bounded, you have an upper bound, optimal upper bound on the volume entropy. And that conjecture says that you should have better, which is if you have a lower bound of the scalar curvature, you should also get an optimal volume entropy upper bound.
So the question was about what does this have to do with hyperbolic geometry? Why does it have to be r greater than equal to -6? Why?
Yeah. So
could you do something? Could you do something with just like r greater than equals to negative epsilon or something like that?
Good question. So there's a lot of good things happening with hyperbolic geometry. So first, the canonical geometry is unique. On the torus, you have all the flat metrics, and also the torus can collapse in many ways, while hyperbolic metrics cannot in many ways. For example, if you just look at the volume entropy of the torus is always going to be 0 simply because the fundamental group of the torus is too small. It's a billion. And so it doesn't really make sense to consider the volume entropy questions in the case of the torus. Maybe, does it answer the question?
Yes, thank you.
Yes, thanks.
Hi, Antoine. I had another question. Could you go back a couple of slides to where the intrinsic flat topology first came on the screen?
Let's see. Yes, here.
Okay, so maybe that was a little too high on the slides list. I'm just trying to understand where is the reason that it appears because it's just the natural notion when you come to do these things in metric spaces?
That's right. So
the Solmani-Wenger.
So there are several reasons. So first, again, the guide is always the finite dimensional case where everything works perfectly well. And there, the usual topology that works the best is the flat topology. So after a lot of work by a lot of people realized that the topology that makes more sense in finite dimension when you try to find a limit of a sequence is the flat topology. And then people consider the, say, infinite dimensional case, and you cannot always get a flat limit. However, if you allow yourself to put everything in a bigger space, a Banach space, then suddenly you always do get, again, this kind of flat limits. So it's really, there were two things. So flat topology in finite dimension, that's really good. And on the other hand, from Hausdorff to Gromach-Hausdorff, that works really well. So people were motivated into defining, like Solmani and Wenger did, they defined this intrinsic flat topology. And moreover, what's essential here is that you have this compactness theorem by Wenger, right? So I remind you that you only need to have bounded mass and bounded diameter. You have some integral currents, they're going to subsequently converge. This is far from being true, of course, if you have a sequence, if you consider Gromach-Hausdorff topology.
So the question was more, why does it appear when you start making those conjectures?
Oh yes. So this is something I unfortunately didn't have time to explain, but what's beautiful in the Besson-Courtois-Gallo result, proof more precisely, is that they reduce this question about the volume entropy into a kind of Plateau problem where they're interested in the infimum of the mass in a certain homology class. What I was interested in is the kind of geometric limits you can obtain. And I remind you that one result is saying that if you look at the homology class they were interested in, and you try to look at Plateau solutions, all the Plateau solutions are intrinsically isometric to what you expect. But what is a Plateau solution? It's an intrinsic flat limit, right? So this is why the intrinsic flat limit comes naturally when you then think about the stability part of the volume entropy rigidity. Does it make sense?
Yeah, I mean, yeah, sure. I don't know this, this area, but yeah.
I mean, that's a follow-up question. My understanding of what you're saying is that if you're just primarily interested in solving this somewhat natural Plateau problem in infinite dimensions, you're saying the only way you can do it is by moving towards this more general notion of what it means to be a minimizer via intrinsic flat topology.
So, yes, I should emphasize that, for example, in this Hilbert manifold, you will have no minimal cycles. So a Plateau solution can never live inside that Hilbert manifold. So in that setting, it's really necessary to get out of the ambient space by using some kind of intrinsic convergence.
So can you go back to what was S star of gamma again, the definition?
For gamma, so if you, essentially it's a unit sphere that you quotient by the regular representation of the group. It's a unit sphere in L2 that you quotient.
Other questions? I'll be willing to try to repeat.
I was able to ask, for the conjecture that you were mentioning, is it also the challenge that you have that unique structure? Is that where the difficulty comes?
The challenge is what?
The difficulty you mentioned too, because you don't have a unique metric, is it falling down to that, or?
Yeah, so the question was about your conjecture in dimension 2. Is the problem related to the lack of unique structure?
Yes, it is definitely related to that. And if you know a little bit about the proof of Besson-Courtin and Gallo, what they reprove is the Mosto rigidity theorem, but that holds only in higher dimension. And they need a so-called barycenter map. And the barycenter map only works well in higher dimensions. In dimension 2, you don't have uniqueness of hyperbolic metrics.
You want to yell it or you want me?
Hey, Antoine, can you go to the slide with the calibration statement? You said hyperbolic metrics are calibrated for your area, right?
Yes.
So maybe a question in the spirit of the CMS, like, is there, how do I say this correctly? Instead of looking at calibrations and minimizers, have you ever worked out like what critical points might look like for?
Yeah, good question. So no, at least in this Hilbert manifold, essentially I just know the following minimal cycle. This is the one that Besson-Courtin and Gallo constructed. So I don't know of any other example, even just of minimal cycle inside that, which is different from this. And yeah, again, one problem to keep in mind is that a minimizing sequence will not in general converge back to this particular submanifold.
Is it easy to describe the calibration?
So it's constructed like that. So you have this, you have this sphere, and roughly speaking, you construct a very nice map that's called the barycenter map that everybody should know of. It's that maps to the hyperbolic metric M. And on M, you have the volume form, right, which is a nice closed form. So you pull back the volume form, it's a nice closed n-dimensional form that's going to live in that infinite dimensional Hilbert manifold. And you can show that this is calibrated, which is amazing.
Hmm.
So this is calibrating, this submanifold.
Anyone else? Maybe I'll throw in one last question. So I happened to see that there was a peak at another slide that said something like general structure theorem, and that sounded interesting. So just so what is that?
Yeah, meaning that, okay, it's good to know some specific examples, like in dimension 3, what's happening, it's nice. But what about in general dimension? And what I would like to quickly mention is that you can say quite a lot about the structure of those Plateau solutions. In particular, they're not just some random integral current spaces embedded in some Banach space. They really are embedded into some, as maybe you can expect, a kind of spherical quotient, even though it's going to be a very different spherical quotient, because in the infinite dimension, things escape at infinity, blah, blah. But it's nevertheless a Hilbert spherical quotient, and you have some variational properties for infinity inside that spherical quotient. This is what I wanted to say. That in higher dimensions, infinity is not just some random space.
Thank you. Anything else?
All right.
All right, let's.
Let's thank Antoine for